webinar of ISPRS Working Group 3.3. My name is Michael Schmitt. I'm from the University of the Bundeswehr in Munich, Germany, and I'm the moderator of today's webinar. And it is my great pleasure to welcome right now 68 participants in this webinar and to introduce our speaker, Professor Florence Tupin. I have prepared a very long biography to introduce her, but I was specifically asked to keep it short, and that's what I'm gonna do. And I think it also makes sense because Florence is very well known in the community and doesn't need any introduction. But for those who don't know her, she's a professor at Telecom Paris, and she's a very renowned scientist in the field of SAR image processing and SAR image analysis. She has published many more than 200 papers, won several prestigious awards, and has been contributing to our society or community in the two different societies, ISPRS and IEEE, for many, many years, acting as associate editor and of course, co-organizer of events, etc. So I'll leave it at that, and I'm very much looking forward to your talk, Florence, on deep learning for SAR image processing. The floor is yours.
Thanks a lot, Michael, for the nice introduction. So hello, everyone. So my talk is a joint work with Loïc Denis, who is invited professor at Telecom Paris, and also Emanuele Dalsasso, who is a former Ph.D. student of Telecom Paris, who is now in Switzerland at EPFL. So my talk is about deep learning for SAR image processing. So you may also find some codes of the methods that I will describe in the talk on this web link, if you are interested. So here is the outline of my presentation. So I will first give a very brief introduction on radar imaging. You probably know very well what I will say, but that will be a brief introduction. Then I will do a short reminder of the statistical model that we can use for SAR images, and I will especially describe the Goodman model. And then in the third part, that will be the core of my presentation, I will describe some deep learning strategies that we may apply when we are trying to do speckle reduction on the SAR images. And then I would like to present you some recent work we did with Loïc and Emanuele, which is a new method which is called MuChaPro, and is mainly focusing on the processing of multi-channel data. So a few words about radar imaging. So as you know, we have a sensor with an antenna, and we are emitting an electromagnetic wave, and that will be backscattered by the different elements that you have on the ground. In the following of the talk, I will consider that we have a nice image, well focalized. We have done the synthesis in the azimuth direction. We have also done the focusing in the range direction, and we have a nice resolution. And for each pixel, we have a complex number. Okay, and why are we using SAR images? So as you know, we have an old-time sensor because we have our own source of illumination with antenna. A very important property that we can acquire images whatever the weather, because we have a wave which is able to penetrate the clouds. And the third point is that we have a very interesting information, which is a phase information for each pixel, and is linked. This information is linked with the distance between the sensor and the target. And as we have seen in the previous seminar given by Ronnie Hensch, we have a very complementary information compared to optical images. But these images, they also have some difficulties. And in particular, we have the speckle phenomenon in the SAR data, which means that we have very strong fluctuations in the physical measurement that we have. So you see here that we have the radiometric fluctuations. And that will be the phenomenon that I will discuss during the talk, and how we can try to reduce these perturbations. So when you are dealing with SAR images, you may handle different kinds of images. So the simplest case, of course, is you just have a single image. So in this case, you will take usually the magnitude of the complex field, and you can just extract information, do object classification, feature extraction. But you also have a situation where you may have two SAR images that the interferometric configuration. And in this case, you will be usually interested in the phase difference between these two images. So on the left, you have the two intensities that you can observe, and then you have the phase difference, which is the wrapped information of the elevation in this case, and you have the coherence information, which is a kind of reliability about the phase information. So that's also a very useful information because it gives you access to elevation or even movement that you may have on the area. A third case is the polarimetric situation, where you are emitting and receiving waves with different polarization. And this time, for each pixel, you will have, for instance, three different complex numbers that will encode some information about the backscattering mechanism that you have inside a pixel. So you have an example of a pulsar image, and the different colors, they are encoding some backscattering properties that you have for the different pixels. Okay, so you have all these different images, and now I will say a few words about the statistical model that you may use for this data. And I will just present the Goodman model, which is a very famous model. So let's go back to the monochannel case. So again, you only have one image. For each pixel, you have this complex number. And usually what you are looking at is just the modulus or the square of the modulus, which is just an intensity data. But as you may see on this image, on the left, you have the optical image, and you have, for instance, this field, which is very physically homogeneous, and you only have a very tight histogram, meaning only one color or one gray level if you are with a panchromatic image. And if you look at the radar image, you see that for the same field, so it's again physically homogeneous, but you have a very wide spreading of all the radiometric values that have been measured for this field. And you see that the distribution is has a very long tail and is very widespread, so it's quite difficult to handle this kind of measurements. And that's the speckle phenomenon. And what is very nice is that we have a very old and very well-founded model, which has been provided by Goodman. And this model is telling you that you have a coherent summation of many echoes inside your pixel, and that you will have, for the real part of your electromagnetic wave, a Gaussian distribution. You will also have a Gaussian distribution for the imaginary part. So you can predict that you will have this exponential distribution for the intensity that you are observing for this field. So it provides you very useful distribution, as you can see here. So here is just the equations of what I've just said before. So let's suppose that my physical parameter of interest is the reflectivity of the scene, which is R here. And I'm just recording, I'm observing a complex field with a real part, which is denoted by A, and the imaginary part B. And you see we have a Gaussian distribution for both of these two different measurements. And if you have an intensity image, which is just denoted by I here, you also have a distribution that will link the observation of the intensity conditionally to the reflectivity of your scene. So I don't want, of course, you to keep in mind all this distribution, but what is important to remember is that we have the likelihood of some observation knowing the reflectivity, which is the physical parameter that we would like to recover in the following. And what is important is that we have also very useful model for multi-channel cases. So for instance, if we have interferometric images, so this time we have sensor number 1 and sensor number 2, and here you have the interferometric phase and the coherence, and you are just in fact computing these quantities which are encoded in the covariance matrix of this small vector, and it will be exactly the same when you have a polarimetric image, except that this time you will have some polarization for the emitted wave and received wave. But again, all the physical parameters of interest will be encoded in this matrix. And you see, again, the Goodman model will give you some distribution that will link the observation, like the small complex vector that you are recording for each pixel, conditionally to what you are interested in, which is this covariance matrix, sigma, which is containing all the physical parameters of interest. Okay, so you have this complex circular Gaussian distribution. If you just take the vector of the backscattered signals, and if you are doing a first processing, for instance, like a multi-looking step, this time you have an empirical covariance matrix, and you have this Wishart distribution that will link your observation to the physical parameters of interest. So again, we are observing K and C, or C, and we would like to recover this sigma information, which is the interferometric phase, coherence, or the polarimetric information, depending on the situation. Okay, so it was just the different expressions that we will need now. But now let's describe the deep learning strategies that we could use to try to reduce the speckle phenomenon. So maybe the first things to say that it's a very, very old problem, and that since the beginning of SAR imaging, people are trying to define ways of reducing these fluctuations, because these fluctuations, they are present in every situation, not only the monochannel case, but also interferometric situation, polarimetric situation. So that's a very important issue. So the oldest methods, they just try to select some pixels and do some averaging, because when you average things, it just reduces the fluctuations, okay? And when you are doing multi-looking, you are just doing some pixel selection, usually just choosing the closest pixel in a small neighborhood around the considered pixels. Later, people have tried to do better selection, for instance, using some selection based on patch comparison, which was a little bit more efficient. So, but anyway, all these methods, they are based on pixel selection. A second family of speckle reduction methods are based on some Bayesian modeling or variational principles. So the main idea is that at the end, you have some energy, and you are trying to minimize this energy by being faithful to the data, but also by injecting some prior knowledge that you have on the images that you would like to recover. But most of the time, this prior information was manually encoded, and it was not so efficient. And of course, more recently, we have the deep neural networks that have given very impressive results to be able to reduce the speckle that you have in SAR images. So I will mostly discuss, of course, these methods. So, in fact, you have many ways of trying to use deep learning strategies to try to reduce the speckle that you have in the SAR images. Maybe the simplest way to do things is to take the second family of approaches, the one I've called Bayesian methods, And inside our energy minimization strategy, we will just use some pre-trained network, because most of the time we need some part of denoising of the image or prior modeling of the image. So we can plug, if you want, a network that has been trained on natural images. But of course, it's not very well adapted to SAR images. So the second level is the most usual way of doing, of trying to reduce the speckle with a deep learning strategy would be to use a supervised training strategy. So the idea is the following. You have some pairs of ground truth and noisy, but I mean noisy is not really a noise, but it's just an image with speckle. And then you try to train a network to estimate, to predict the reflectivity, which is the physical parameter you would like to recover, by comparing the output of the network to the ground truth that is available. Okay, so it's very simple. You are just doing a comparison and you are adjusting the parameters of the network to have a nice image, which is similar to the ground truth. But you have two main difficulties to use these supervised training frameworks. And the first one is that with SAR images, you do not have any ground truth images, because each time you are taking a SAR image, you have this coherent imaging process that is appearing, and you will have the speckle phenomenon in your image. So, of course, you may say, okay, I don't mind, I will use optical images, panchromatic optical images, and just say they look like SAR image. But you can also do some multi-temporal averaging, or you can also do some strong multi-looking to try to obtain ground truth image. But even if you do that, the second difficulty is that it's not so easy to simulate the speckle on your ground truth image to create the noisy image. Okay, we've seen that we have the Goodman model. So Goodman is giving us the distribution of the speckle. So you may think it's quite easy. I just have to multiply my ground truth image with the speckle. But the main problem is that the real SAR system, they have some point spread functions. They have some kind of multi-looking processing, oversampling, apodization, many different processing that will not really perfectly fit usually to your speckle simulation. So both the ground truth is difficult, simulating real SAR images with the right PSF is also quite difficult. So this strategy usually will work well with synthetic speckle, but they will not be so good. And usually you have some artifacts when you apply them to real SAR images with some real sensor. So I will mainly describe another family, which is the family of self-supervised training, okay? And before diving in the different strategies that you may apply to do this, this kind of processing, I would like to present first this work of Lehtinen and co-authors, which has been published a few years ago, and which is a very interesting work. And what they showed inside this in this paper is that you don't really need ground truth images to be able to train a network. Instead of using pairs of ground truth and noisy images, if you have access to pairs of noisy image of the same area, the training of the network will be the same. If you have enough samples, the parameter that you will obtain for the network will be exactly the same if you train on the ground truth image or if you train the network using another noisy realization of the scene. Of course, you have some assumptions that have to be verified to be able to obtain these results. And the first one, of course, is that the two noisy images have to be correspond to the same ground truth image. Even if you don't know it, they have to be noisy realization of the same ground truth image. The second assumption is that they have to be, the noise realization have to be independent between your two realizations. And the third point is that you have to adapt the loss function when you are using this kind of strategy, because this time you are not comparing a predicted output and the ground truth, but you are trying to evaluate the likelihood of the noisy image compared to the predicted reflectivity that you have estimated with the network. So be careful here. You have to modify, and usually a good way is to try to maximize the likelihood of the second noisy image compared to the output of the network. Okay, but this work of Lehtinen noise-to-noise is a very good framework for SAR images, because if we are dealing with satellite images, the satellite is coming back after a few days. So we have a new acquisition of the same area on the ground. So we could use these two different dates to train the network. So we put a noisy image in the input of the network. We try to have some prediction of the reflectivity, and to do the supervision of this output, we are just trying to maximize the likelihood of the second date that has been acquired for the same area. So it's really a nice framework. You don't need any ground truth image. You just need to have some pairs of SAR images of the same area on the ground. But of course, you have to be careful, because you may have some changes between the two acquisitions. And if you have some changes, you have to find a way to correct these changes to be sure that you are having the same information that is encoded in the two images. So what we have proposed is a way of doing the change correction inside this network. And to do that, what we have proposed to do was to do a first coarse estimation of the reflectivity of the scene, and then to do a correction of the image so that to make it similar to the date that is given as input to the network. So what we do, if we have a second date, we first subtract, because we are working in the logarithm domain. We are first subtracting the reflectivity, the coarsely estimated reflectivity, and then injecting again the reflectivity similar to this one. And in this way, we can have a good supervision of the network, because we have compensated for the different changes that we may have on the scene. So here is an example of this method, which is called SAR to SAR. And you see here you have a Sentinel-1 image. Here you have the denoised image. And what is nice is that you only need to have some pairs of images to do the training of the network. You can, of course, do the training for different sensors. You only need to have these pairs of images. And here is a training devoted to ground range detected images, because this time you do not have exactly the same statistical model, because for the GRD image, you have a multi-looking processing which is applied, and that you have to take it into account to do the training of the network. And of course, this can be useful to do downstream tasks like river segmentation or things like that. Okay, you can extend this kind of methods to multi-channel case. So it's what we have done recently with this polarimetric version of SAR to SAR, which is called pulsar to pulsar. There is the main framework is exactly the same, but what is difficult in this polarimetric framework is that you have to reformulate the change compensation when dealing with the polarimetric covariance matrix. So that's the main difference between these two processing. And we have also proposed another recent extensions to this method, but this time for interferometric images. And in fact, it's not so easy to use this framework for interferometric images, because you usually do not have the same area with exactly the same configuration of your two interferometric sensors. But what is nice with Sentinel-1 data is that you have an overlap between the different bursts that are acquired. So what does it mean? It means that for the first acquisition, the first date of the interferometric pair, you have some part which is overlapping. And for the second acquisition, you also have some part which is overlapping. So you can take the overlap of the bottom part of this top burst to create an interferometric covariance matrix. And you can take the top part of the bottom burst to have another one. And both of them will encode exactly the same interferometric configuration, exactly the same configuration on the ground with the same atmospheric perturbations. Everything will be similar. But since you have a slight in different incidence angle between the top part and the bottom part of the burst, they will look like two different realizations of the speckle noise. So you can, again, use the noise-to-noise principle to do a training of the framework on the real images. Okay, so here you just have an example of this method, which is devoted to Sentinel-1 images. So here you have the original phase and the restored phase by the insert to insert method. And here you have the coherence image, and you see that we have a clearer demarcation between the low coherence and high coherence parts of the image. Okay, so let's move to, but you may say, okay, but we need two noisy images, and maybe we don't have two pairs of images very well registered in almost the same conditions, even if we have the change compensation. So what about a real self-supervised strategy? So if you only have one image and you want to train a network, you still have different ways of doing that. So one of them is to use the spatial diversity. So you will mask some of the information. So you see, for instance, the blue point here, and then you will train the network to predict the value for these masked pixels. And then again, you will try to maximize the likelihood of the hidden values with the noisy information. So it's what is difficult in this kind of strategy is that you need a specific architecture not to see the masked pixel at any step of your deep learning when you are doing the training. And the other point is that, as I've said before, because of the PSF of the sensor, you usually have some spatial correlation of the speckle. And that's something that you have to take into account when you are trying to train this kind of networks. So what I would like to present here is another strategy, which is very nice because it's very simple. It's just to take the SAR image and split the image in two parts, in the real part and an imaginary part, using the complex value of each pixel. So what do you do in this situation? So you have a complex number. You take the real part and you put it as input to the network to try to do some prediction of the reflectivity value that you are interested in. And to supervise this output of the training of the network, you will again try to maximize the likelihood, but this time of the imaginary part of the image that you had at the beginning. So why is it working to split the real and imaginary part of your complex image? So this time you just have one image, so it's very easy to train. Why is it working? Again, because of my Goodman model. You remember at the beginning I've said, oh, I will have some statistical modeling and I have some independence between the real part and the imaginary part conditionally to the reflectivity, which is the parameter we are looking for. So what does it mean? If you take the likelihood and you take the log likelihood and you put a minus sign because you are minimizing a loss, you will end up with this very simple loss, and you take the real part, you give it as input to the despeckling network, and then you will try to minimize this loss by just comparing the imaginary part to the estimated reflectivity. And what is important is that the despeckling network since he has no access to the imaginary part, he has no better guess, if you want, than just trying to have a good estimation of the reflectivity if both of them are independent. So what happens if you are training a network in this way? When you are in the testing part, this time at inference time, you will have a first prediction using the real part. You will have another prediction using the imaginary part. And you can have a final estimation by just combining the estimation based on the real part and the one estimated using the imaginary part. And in fact, this method is very efficient. You don't need any pairs of images. You just take many single loop complex images and you just feed them to the network to train the network. And of course, you have plenty of such images. So here is a result for TerraSARX images. So here you have an intensity image. So as I told you, we will split the real and imaginary part. And for each of them, since we have trained the network, we can do a prediction that you see here. And then they are both combined to have the final estimate of this first intensity image. And you see you have both a strong reduction of the fluctuation of the speckle, but you also have a very good preservation of the bright targets and the linear structure that you have in the image. You can also apply this kind of strategy even if you're in urban areas, and you see that it will again give you quite good results with a well preservation of the different bright targets and stronger scatterers that you may have in urban areas. But what I must say is that you have to do the training for each sensor, right? If you are dealing with TerraSARX images, you have to do the training for instance, the spotlight mode, the ScanSAR mode, and so forth, because for each sensor, you will have some new set of weights that is adapted to the different features of the sensor, let's say. So here is another example with the aerial image of Onera. And you see you have even a finer resolution with very accurate, very fine structures on this image. And you see again that we have a good restoration of this kind of information. Okay, I would like to take a few minutes to speak about this new method, which is called MuChaPro. And I will first try to motivate this work. So we've seen that we had different strategies to do the training of the network to try to reduce the speckle in the SAR image. Many of these strategies can be used for multi-channel images. For instance, it's the case for this pre-trained network. You see I put some reference here where we did some extensions to the polarimetric case. Even for the temporal diversity, you can adapt it to polarimetric images or interferometric images. But you see this the last method with the real and imaginary part splitting, it's the most efficient one because you don't need pairs of images, you don't need ground truth, you have no modeling as you have in this energy minimization approaches. So what we wanted to do was to be able to exploit this framework, even in the case of multi-channel images. And the solution we ended up is this one. And the idea is very, very simple, but at the same time very efficient. And the main idea is to use some projections of your multi-channel data. So let's take the example of an interferometric configuration. So in this case, I have two images, for instance, taken at time 1 and time 2, and I'm trying to evaluate the interferometric phase, the coherence, and the reflectivity, which just the evaluation of the covariance matrix 2 by 2 associated to this information. So how could I use my Merlin method, which is the one which is splitting the real and imaginary part? So the main idea here is that we can create many single look complex images by just combining these two original complex images. So you have different channels, and you can combine these channels, for instance, by adding them or subtracting them or doing any linear combination with complex coefficients of these two channels, okay? So it just, this operation is just a projection of the original channels, but using different projection vectors, right? And then now you have many single look complex images. And what is nice is that we've seen previously that Merlin, for instance, but it can be another method, is a very efficient way to be able to estimate the reflectivity of all these channels, right? So I can restore all these projections and I will have many evaluations of these different reflectivities. And what is important is that these new reflectivities, in fact, they are linked to the covariance matrix coefficients by some explicit formula, which depends on the projection. So I can recombine all these projections to obtain for each pixel restored covariance matrix. Okay, so in fact, this method is very simple. You just create a certain amount of new single look complex images. You will suppress the speckle in the best way as you can for all these images, and you will recombine all these projections to obtain the covariance matrix that you are interested in. Okay, so let's just give you a few more details about each step. So this time, instead of just having one complex number for each pixel, I just have a small vector with a dimension d, which was just 2 in my previous example. And I know, using Goodman model, that this vector is following a complex circular Gaussian distribution with some covariance matrix that I'm looking for, right? So now let's take some vectors in the same dimension as the original data. And let's do some projection just by combining the different channels, right? So now I have a new complex numbers for each pixel. And what is important is that the reflectivity that I could estimate for this complex number is linked to the covariance matrix that I'm looking for, thanks to these projection vectors that I have used to create my new image, right? So there is some explicit formula between the reflectivity of this new image and the covariance matrix. Okay, so now what I will do is to try to find an estimate of this reflectivity, because I will be able in this case to have some link between this reflectivity and the coefficients of the covariance matrix. So you can use some speckle reduction for the multiple projections. So you will have some estimation, and each of these estimation of the reflectivity give you an estimate of some projection of the covariance matrix that you are looking for. And what is very nice is that, in fact, you can have an explicit solution to recover the covariance matrix. For instance, you can choose to minimize the error and use a linearly square minimization to obtain an estimate of this covariance matrix. And there is an explicit formula that is given in the paper. So if you have estimation of this new reflectivity, just by despeckling the different images that you have created, you can go back to the covariance matrix that you are looking for. Okay, so at the end, you take your single look complex channels, you just do some combinations between them using some projection vectors, you do the restoration of the projection, and you have an explicit formula to recombine this projection to obtain the estimation of the covariance matrix. Okay, so what does it mean in practice? So here is the results of this method, using the Merlin method to do the denoising of the different images that we have created. So here you have the result of the multi-looking. you have the polarimetric estimation using a 5x5 multi-looking in a square window. And here you have the estimation using this multiple channel projection approach using the Merlin denoiser as the denoiser for each single look complex image. And again, you see that you have a strong speckle reduction, but at the same time, you have a good preservation of the different fine details that you may have in the image. So here you have an example. In this example, we have used 4 projections, meaning that we have used 4 vectors to create these new images. And here you have the denoising of each image. I just show you very quickly, an example for interferometry. So here you have 2 terrassar images of a mountain of the Jungfrau Glacier. Here you have the coherence and interferometric phase. So glaciers are not very coherent, so that's why it's quite noisy, except on the rocky part. And here is the original 5x5 interferogram that you can estimate. So you see that you still have some noise in different parts. Okay, and here we have applied MuChaPro, so on the 2x2 matrix this time. So we have created 4 different projections that have been denoised and recombined. And here is the diagonal element of the covariance matrix, which is just the reflectivity for the first date and the reflectivity for the second date. So you see that you have a strong denoising. You can also have a look on this zoom image. So again, you have a strong speckle reduction, but at the same time, a good preservation of the different details that you have in the image. So here is the over date, and here is the interferogram, and you see that you have mostly an enhancement of the different interferometric with a good restoration of the interferometric phase. So just to conclude this talk, so in fact, deep learning methods, so I've only presented a few parts, of course, of the method that exist to do speckle reduction, but they really provide state-of-the-art results. So MuChaPro is a very efficient method because you don't need supervision, you don't need pairs of images to do the training, and you can leverage a single channel denoiser at Merlin, as we have seen before, and it provides very efficient results. But my main message for the end of this talk would be to say that, well, I mean, speckle reduction, it can be of interest for some thematic applications, but of course, the speckle reduction, in fact, is useful beyond just the speckle reduction itself, because the representations that are learned by the networks during the speckle reduction task, they are also very efficient for other downstream applications. So I had not time to describe other works we did, but for instance, the denoising task can be very useful to help segmentation or elevation recovery, even if you have very few labels. So in the case when you are in weakly supervised framework, it can be very useful to do jointly the denoising on the downstream task you are interested in. Of course, the deep learning methods can help you for many other different applications like tomographic inversion. I just put an example here, and it can also be a very interesting research topic is the NERF-like strategies to try to find elevation combining different views that may be available even with different sensor, maybe using SAR on optical images. So that's also very interesting fields of research. And just to conclude, I would like to thank some of the, at least to acknowledge some of the fundings we have received. And again, you can find some of the codes that are associated to the papers on this web page if you are interested to try some of them. Thanks for listening.
Thank you very much, Florence, for this very interesting talk. on your excellent work on self-supervised learning for SAR image analysis. I really love it. And I believe also the audience loved it. We were at more than 90 participants during the talk. And also we have received already quite a number of questions. And I would now like to start directly passing those questions on to you. And I start with one question sent in by Udit Azopa, because it's a very fast one. The question is, what exactly is meant by multi-channel? Is it multi-pol or time series, or what exactly is meant by multi-channel?
Well, indeed, it can be different situations. Here, I'm mainly focused on interferometric situation, tomographic situation, but it can be also not tomography, sorry, polarimetric, but it can also be the combination between interferometry and polarimetry, SAR, for instance. For tomographic configuration, you can also try to apply this kind of things, but you soon have lots of channels, and so, okay, but you can still apply this kind of framework, of course.
So in the end, it's different combinations of SLC images channels.
Yes, yes, mostly interferometry and polarimetry and multitemporal. You can also apply them, but you will soon have some decorrelation usually between them. So,
thank you. I think this answers the question perfectly. Then we have another question by Juan Francisco Amieva. And here the question is that they have already worked with Merlin. And the question is about input requirements. So is it necessary to calibrate the input images before using them with the model? Or should Merlin be directly applied to the raw SLC files? So is there any pre-calibration necessary?
Okay, so I'm not exactly, so that indeed it depends what you want to do. So if you just want to use some weights that have been provided on this web page, for instance, you just have to be careful to be exactly using the weights for a specific sensor and a specific modality for this sensor. So just check that. And if you want to do your own training on your own single look complex images, the conditions are the following. You have to check that the spectrum of your image is perfectly symmetric. Okay, it means that, for instance, if you are using Sentinel-1 images and you want to do training, normally you have to do a deramping step because of the top SAR mode, for instance, and you have to find a way to symmetrize the complex spectrum of your image, because that's one of the conditions that is necessary to have the independence between the real and imaginary part. So the main condition that you have to verify is on the complex spectrum. But I think you were mostly speaking about the calibration or the range of the images. So what is important is that if you do the training with a certain range of values, you have to keep it when you are doing it at test time, for sure. And if you are just taking the weight that, for instance, we have provided or someone provide, just check what is said about on which data the training has been done. Because you can do or not a normalization. I mean, I would suggest not to do any normalization of the data, but it means that when you are at test time, you have to have exactly the same kind of data. And I don't know if it's clear.
I think I can also, let's say, add to it. So in our experience, if we train deep neural networks on large amounts of SAR intensity imagery, we typically estimate the average histogram of the intensity values we use throughout training. So we get like a mean histogram of those of the training set. And then if we use our network on new data, on unseen data, we typically do a histogram matching, so that the histogram of the test image is more or less equal to the histogram of the training set. And maybe this is what was being meant.
Yeah, that's also a good answer.
Okay. Then let's see, what is the next question? We have another question by Avinash Mahet. You show a large variation of amplitude in the histogram plot as compared to optical data.
Yeah.
I have also observed this in my case studies where I noticed large variations in pixel values with common land characteristics, even in nearby features like lakes or river bodies. How can these challenges be addressed? Asks Avinash Mahesh.
I mean, normally the speckle reduction should work whatever the kind of area that you are processing. Maybe I didn't catch exactly the question. I mean, it should also work on rivers or on lakes or.
I'm also not sure whether I understood the question correctly. I believe it aims at that homogeneous areas have strong gray value variations, whether this causes a problem or not.
I mean, we yes, that's exactly what you observe with the SAR images. But normally, these methods they should be able to reduce it to whatever the kind of if the Goodman model is verified.
Okay. Then we have another question by an anonymous attendee. Did you ever observe any artifacts in the results of the Merlin filter? Because this person said they experienced some artifacts in homogeneous regions. Also, they observed a tendency to smooth out point features, especially when located close to each other and aligned, causing them to appear as line features after the filtering. Did you observe anything like that?
Well, for the artifacts in a homogeneous area, my main experience is that people try to apply some methods that have been trained on white speckle, and they do some training of the network, and then they apply this network on images where the speckle is spatially correlated, and that will create artifacts. So that's why I really insist, if you use the code, or even if you do your own training, if you do the training for a sensor, it is robust only for the same sensor, because it's taking into account the spatial correlation of the speckle that is in the data that it has been trained for. So please do not do synthetic speckle and then try to apply it on. Okay, just be careful about that, because that's a very important point. And to answer about the strong scatterer that you have in urban areas, it really depends on the training set that you have used. And for sure, you need the more data you have with the more situation of this bright point configuration, the more accurate will be the trained network.
Okay. Next question comes.
I would suggest to increase the training set.
In that context, maybe quickly from my side, do you share the weights of the networks you train, or do you keep them internal due to, let's say, data licensing reasons?
I mean, some of them can be found on the Ring, this Ring GitLab. Mm-hmm. But just be careful. We've had, for instance, a training for Sentinel-1 data in top SAR mode that should be applied exactly on that. And for instance, for TerraSARX, it's not the same weight for Spotlight and for ScanSAR and things like that. So I don't remember exactly in which situation, but yes, normally many weights have been provided. Emanuele should be, I think, in the seminar, and he put some weights of our trainings.
Okay. Then we have questions from Georgios Kouroupis. The question is, can we use these INSAR time series to alleviate the SBAS short baseline drawback with temporal coherence over vegetated areas? Maybe that's a bit out of direct scope, but maybe you can try to answer it if you want.
Anyway, I think it should be worth to see if this kind of speckle reduction method could help differential interferometric methods. We have not really worked exactly on specific application like SPAS and so forth, but I think it should be helpful.
And the second question would be, if MuChaPro is applied on a quad pulsar data set to the noise per polarimetric channel, does the end result, so the combination of the denoise channels, respect the original polarimetric properties in terms of incoherent or coherent target decompositions?
Yes, it's what we are trying to verify when we are processing polarimetric data. MuChaPro is very recent, so we have not done careful evaluation on polarimetric quad pole images anyway. We have some radar stat images or RCM images, but we have not investigated, but of course it should respect the polarimetric behavior even after denoising, and you should not have biases or modification of the polarimetric responses.
Yeah. Then we have a question by Kiyoshi Honda. Do you think the method is effective for change detection, such as disease detection in crops, which changes structure and shape of plants? So this question is really aiming about very detailed detection of changes.
Well, we are working on change detection. We have some Ph.D. students working on this subject, and we are using the deep learning methods to have some improved input to the change detection method. And what we are doing is to try to associate to the reflectivity estimation some quantification of the uncertainties that is associated to the despeckling, and this is then used in the change detection method. You can send me an email and I can send you some reference if you are interested.
Very interesting. Yeah. My question would have been whether it makes sense to go this intermediate step of denoising instead of doing end-to-end change detection, but if you have basically answered my question already by saying you do it via uncertainty estimation, then it makes, of course, sense. We have another question by Yusuke Adachi. Is the MuChaPro method better than Goldstein and Wiener filters for INSAR applications?
I think so.
Yeah, I also think so.
But you can check.
And then Salah Ben Mamiut asked a question that we have already discussed. Does the input image to the model require pre-processing or not? So I think we have already answered that. There's some match of the distributions necessary so that you don't end up putting out of distribution data into the model.
You have a discussion about that in some SAR paper of Emanuele, where he discussed the conditions for SAR to SAR, the conditions for the blind spot methods, and the conditions for the Merlin method about the spectrum and the symmetry that I have spoken about.
Yeah. And then Kunal Bansal asks, how does this method contribute to studies relevant to urban applications?
Well, I think that this method should help to, well, for instance, at the end of the talk, I've spoken about this footprint, building footprint detection, and also elevation estimation, as you have proposed, Michael, in the IM8 framework. So what we did is to combine the despeckling of Merlin and this elevation estimation or the building footprint detection, and really combining the despeckling method, even if you are not interested in the despeckling part in itself, is helpful for the downstream task of building detection and elevation estimation, because the representation that is learned is very efficient to help the other tasks. Yeah. So it's Merlin SEG8, and you can also find them on my webpage or the one of Emanuele.
It's kind of a very, very powerful auxiliary task, if you want, in a multitask setting. And then I overlooked one question by Wataru Takeuchi. Would you say that your techniques improve the ability to detect landslides in sloped areas?
I hope so, that it could be helpful because, okay, that's differential interferometry, and probably we could, yes, well, my feeling is that it's very easy to train this network because, for instance, for Merlin or MuChaPro, it's really not for free, but I mean, it's not so difficult to use these training methods. And then you have much, you have measurements with much less variations, so that are much easier to handle for applications. So I'm really convinced that it could help for many applications.
So am I. Thank you to everybody who asked questions so far. It seems that there are no questions anymore. Oh, no, there's one additional one coming in. Very specific. Pratyush Das asks, any suggestion how one can use these methods for speckle filtering in context of CARD4L compliant Sentinel-1 data? To be honest, I do not know what CARD4L, CARD4L compliant Sentinel-1 data is.
I don't know. Maybe you can send me an email.
Yeah. Maybe Pratyush Das send an email afterwards to Florence Tupin. And then we have another question by Sripriya Darshini. For stormwater drainage, which method would you say will be effective?
Sorry, which method?
If the application, if the task is stormwater drainage mapping, I presume, which method would be most effective?
Well, it really depends on the data you have at hand. So is it, for instance, many people work on GRD images. So in this case, for instance, we have the SAR to SAR framework, which is very, very adapted. If you have single loop complex image, I think that Merlin can be trained so easily if you have plenty of images. So it really depends on the data at hand that you have.
Yeah. And a very similar question again by Wataru Takeuchi. Is the technique effective in determining damage to buildings destroyed by earthquakes? And if not, what technical developments do you believe are needed to make the method feasible for such, let's say, change detection scenarios?
Well, we have started working on that, but it was a very small project, and I think it might help, but I'm not sure it completely solves the problem because some of the damage were very difficult to recognize in the SAR image. So probably it's not enough, but at least it can help to a certain extent to use this kind of speckle reduction methods in collaboration with the other channel detection method.
Okay. Now I believe all the questions have been answered, and I'm really thankful and grateful for the many questions that have been provided by the audience. So it shows that there is great interest in your work. And it's also great that you share codes and weights and lots of open access material so that the community can build upon your research results. Thank you again for the talk. And because there was the question earlier, my understanding is that the recordings of those webinars will be shared online on some ISPRS Student Consortium pages. So you will be able to rewatch.
Okay. Thank you all. Bye-bye.
Thank you. I'm closing the session now. Bye-bye.